Okay, SPH3U, this is the last video in the energy unit, and we're talking about electricity generation. So we're going to put together a lot of the stuff we've been learning about and talk about efficiency and power and thermal energy and all that stuff. Here's our curriculum expectations for this part of it, which technology that transforms or transfers thermal energy. A lot of our power plants use thermal energy. The impact on society of nuclear, thermal, or geothermal energy technologies. And finally, explain the energy transformations that occur within a nuclear power plant. So a lot of this is going to be about nuclear power. Pull up the learning goals. First off, we're just going to learn about the basics of power generation, turbines and generators and stuff. We're going to jump into just solar, hydro, and wind to get those out of the way. Then a brief detour into nuclear weapons, because I want you to understand the nuclear chain reaction, and then the nuclear power generation itself. And then finally, the thermal energy plants, fossil fuels like coal and gas and stuff like that. And then the very last piece is peak energy and energy storage, which is a relatively new idea. So take that away, and let's get started. So first off, I'm going to move my thing down to the corner here. We make electricity most of the time by turning a generator, and this is what a generator looks like. It's just a big coil of wire. It's a big coil of wire that's turning, and there's magnets around it, and turning that in the big coil of wire makes electricity. You might have like one of those flashlights that you crank at home that'll have something like this in it. It's just a generator. Humans are very good at building generators. We've known the basic physics behind them for a very long time, and so they are over 98% efficient at turning rotational energy into electricity. So rotational energy comes in, electrical energy comes out. 98% efficiency, only a 2% energy loss, which is really great. So if we can find a way to turn something, and make electricity, we're going to do it. Now, finding the way to turn something becomes kind of the sticking point here, because let's say you have steam power. Steam power comes in, it wants to just go in a straight line. The steam just wants to go straight down the pipe. So what they have to do instead is put something that turns in the way, kind of like a windmill or a propeller or whatever. This is called a turbine. A turbine is something that takes linear motion and turns it into rotational motion. So it takes kinetic energy and turns it into rotational energy. And then there's the generator back here that's doing the job of turning that into electrical energy. So kinetic, rotational, electrical. Now, turbines aren't that efficient. So even with our best efforts, we can maximum get something like 60% out of a turbine. So typical steam turbine, which is like this turbine that's being powered by steam, is about 50% efficient. A wind turbine is about 40% efficient, depending on the turbine. Here's a picture of a turbine. All right, and you can see these are people. So these things are huge, and it's just a bunch of fans in a row. The steam hits one fan and starts turning it, hits the next fan and starts turning it, and stuff like that. Geothermal, the turbine is only about 15% efficient because there's a low pressure difference, because geothermal has a small temperature difference between the hot and the cold. The bigger the temperature difference between hot and cold, the more efficient your turbine gets, basically. Basically, the faster that you can get the steam or air flowing past it, the more efficient the turbine gets. Hydro turbines, in the meantime, get to enjoy a nice 90% efficiency. Why? Why is hydro so much more efficient than steam or air is kind of the question that I'm asking you guys. And think about water versus air and how easily they can transmit their kinetic energy to you. Right? So the air can blow at you, and maybe it's going, maybe it's like a really windy day outside. It's like 60 kilometers an hour, and the air is hitting your face at 60 kilometers an hour. Well, that's fine. You might have a hard time standing up or something, but if water hit you at 60 kilometers an hour, you'd get knocked over. Water is just denser, carries more mass, and more mass means more energy per unit volume. So the water can more efficiently turn the turbine. It's also important to note that water is incompressible. You can't compress it the way that you can compress air. And so the turbine can really get in the way of the water. Whereas with air, you've got compression issues. Yeah. So most power plants that use turbines, especially gas and steam turbines, will end up being about 30 to 40% efficient. Everything else is just heat. Um, yeah, everything else just gets turned into just wasted heat. And because turbines and generators are so common, right? Here's the turbine, here's the generator, here's the turbine, here's the generator. Um, Being able to turn a turbine is is a really good way to make energy. We understand that energy concept very, very well in terms of the engineering required. So all you have to do is get something hot, turn water into steam, that steam drives a turbine, the turbine drives a generator. Every time. Right? So here's a coal power plant. The coal comes in, it gets burned for energy. The thermal energy heats up the water turns into steam turns the turbine makes electricity, turbine turns the alternator makes electricity. Steam comes back, gets heated up again, and there's the loop. In the nuclear, the thermal energy comes from the nuclear reaction rather than a chemical reaction, but it's still just thermal energy. It gets carried over to this by a pipe that's carrying hot stuff. That turns this into steam. Steam comes over, drives a turbine drives a generator, out goes electricity. Water comes back, and then the water gets shoved back in here to get turned back into steam, and then it just repeats over and over and over again as long as there's a nuclear reaction happening in here. And it's always the same loop for both. They both have the same basic operating principle. They differ in how they make the thermal energy, or how they release the thermal energy, where it comes from. They both have to deal with extra thermal energy because they have to cool this back down before it can come back in here to heat up again. So they usually just exchange it with the outside world, sometimes in a big cooling tower by running it through a condenser, and sometimes in just a water pool, just a big pool of water. Notice though that this water doesn't touch the nuclear reactor, and this water doesn't touch the actual coal part of the thing. It's a way to separate. You're transferring the heat. You're not actually transferring the working fluid. You're doing it by conduction instead of by convection, which is pretty clever. Okay, hey, that's the end of the first section, talking about efficiencies. Here's some various efficiencies just to look at them. Look at hydropower, just by far and away the most efficient power generating technology. Way at the bottom here is geothermal and solar panels. Photovoltaic means solar panels. Solar thermal is a little bit better than solar panels. We'll talk about solar thermal. Here's some combustion engine generators. You might have a generator at home for power outages. That's this thing. It's actually more efficient in terms of heat loss than a solar panel would be. Diesel's even better. And then we get up into wind turbines, about 30%, 35% efficient. Coal plants are up here. Nuclear is just above wind, also in that 30 to 40 range. All of these use turbines, and most of them are gas-driven turbines or steam-driven turbines, and so they all end up being very similar efficiencies, and that's limited by the turbine efficiency. So that's that. That's the first section. Check that off the list. All right. Next up is solar, hydro, and wind. So I'm going to pause and redo my thing. Never mind, I realized it was already on screen. So let's just keep on going then. So solar power. Solar has two kind of modes. You can have the solar panels that you're probably used to. That just takes light energy and turns it directly into electricity. It's only about 15 to 20% efficient. So you need a lot of solar panels to make any amount of electricity. You basically have to cover your entire roof in order to make enough for your house. Stuff like that. The other type is solar thermal. This is a solar thermal power plant. And a solar thermal power plant, it takes mirrors. It focuses the light onto something and makes that something very, very hot. Just like taking a magnifying glass and making a hot spot. But that hot spot, they'll circulate fluid through there. The fluid gets hot, turns into steam, turns a turbine turns a generator, you make electricity. So it's basically one of these, right? It's basically one of these except for the thermal energy comes from the sun instead of from a chemical reaction or a nuclear reaction there. This is a real picture of one of them in China. You can see that it's so bright, the focusing is so bright that it actually glows. You can see the air glow around it. The towers are about 30% efficient, so they're better than a typical solar panel. This is a different kind called a trough solar thing, where they're focusing it just onto this little pipe, and that's heating up the fluid, and that's going to go and turn the turbine. This is less efficient because you don't have as much area heating up in one spot. It's like trying to do the magnifying glass thing with a smaller magnifying glass. You won't get as hot of a spot. We're going to talk about advantages and disadvantages. The advantages, obviously, there's no greenhouse gas emissions, except for when you're manufacturing the things. You're taking out the silicon and stuff from the ground will release greenhouse gases, but after they're installed, that's fine. One major advantage of solar panels in particular is you can just plop new solar panels down. You don't have to go out and make like a hydro dam or a nuclear station or anything like that. You just stick a panel in, connect it to the electricity, you're good. So that makes it a good option for houses. Disadvantage, it only works when it's sunny, so you still need a way to get electricity at night. Some people, do the solar panel and then they store the energy in a big battery. It requires a lot of special materials to make because these things, they're electronics, so you need special materials. And solar thermal, this stuff takes up a lot of land. Not a problem if you've got a bunch of desert to work with, like here in China or here in Los Angeles, or like outside of Los Angeles, there's one of these. But if you're in a place like Hong Kong or something like that, you're not about to make a solar power region. Yeah, that's solar. Next up is wind. Wind is, big fan blade, turns the turbine. So this captures the wind energy, turns a turbine turns a generator makes electricity. Efficiency limited by the power of the turbine. It's about 40%. But lots of advantages. First off, no greenhouse gas emissions, just like the solar panel. It can work day or night, which is a big advantage over the solar panel because the wind will blow at night as well, which means it can be more reliable than solar. You can also put them offshore if you don't want to use a bunch of land. You can just use your ocean for it, right? Not a big deal. Disadvantages, only works when it's windy. So if you've got sporadic wind, it doesn't work super great. There are certain places in the world where there's a lot of wind, and so it's easy to put turbines there. Sometimes you'll see them up on top of hills where there's a lot of wind up on top of the hill. It takes a lot of resources to build. Like, these things are massive, absolutely massive, so you have to have access to where you're placing them. They can also be a nuisance to nearby houses. So I found this YouTube video that I'm going to show you guys over here. This guy that lives near a wind turbine, and in the mornings when the sun lines up with the turbine just right, so you see the sun lining up with the turbine just right, this is called shadow flicker. And you see it flickering across his house. Right? Flickering across his house. And you see it flickering across this house as well. And then he goes inside and shows you what it looks like on the inside. So there it is on the inside of his house. Okay. And here's what it looks like, when you're further away from the window. So imagine that for, a certain amount of time every morning. So that can be a nuisance. That's shadow flicker. And it also kills birds and bats. Wind turbines do kill a lot of wildlife. The air pressure behind the blade is much lower than the air pressure in front of the blade, and that sudden drop in air pressure will mess up the lungs on birds and bats. They have very sensitive lungs. And so these things do kill a fair amount of wildlife. Yes, that's wind. Next up, hydropower. Hydropower just has water up high. The water wants to go down low. They make it turn a turbine. It's extremely efficient, over 90% efficient, because water is incompressible and heavy, and so it can turn the turbine very well. Advantages for this is you can have a lot of power capacity. You know, if you have the environment for it, you can have a ton of installed power. Quebec actually makes more than 100% of its power through hydro. It sells the rest to the states and stuff like that, and Ontario too. It actually sells power to us. It works day or night as long as the water's flowing. It's working. There's no greenhouse gas emissions except for building the thing, which actually does release a lot of greenhouse gases because of all the concrete and the fact that you have to flood a big reservoir. So that's a disadvantage. Disadvantage, first off, lots of time and a lot of resources to build because it's a huge concrete structure. It also has to flood a big reservoir. So here you can see before they installed a dam and after they installed a dam, it floods the area. And so there were people living here that had to get displaced, and wildlife and stuff that have to get displaced. Stuff like that. They're also only good in certain locations. You need a height difference and you need running water. So, you know, that's not great. Another way to do hydropower is tidal energy. So the tide comes in and fills up your reservoir, and then as the tide comes out, you can let it through. You can get a lot of power capacity out of this. It also works day or night because you're just storing it up and you're just letting the ocean refill your reservoir. And there's no greenhouse gas emissions for building. Disadvantages, same thing, a long time to build, lots of concrete. And you're also blocking access to the ocean wherever you've built your tidal dam. And that means it's only good in certain locations. You need high tides and you need a place where people don't need to access the ocean in that area. But there are tidal power plants here in Canada, you know, out in the Maritimes, where they have very high tides in the Bay of Fundy. Yeah, that's that. Next up, we're going to talk about nuclear bombs. So let's pause, and I'm going to fix this up. Okay, I'm back, and we're talking about nuclear bombs and criticality. This diagram shows you what I mean by criticality and the nuclear chain reaction. This is the fission. Remember, we learned that word fission of a uranium-235 nucleus. It gets hit by a neutron, turns into an unstable nucleus, and then splits into two, and that makes 3 neutrons. Those neutrons can hit another U-235, which splits, makes 3 neutrons, which hits more U-235, splits, makes more of those. And this is called a nuclear chain reaction. So that's a nuclear chain reaction, right? It's splitting and then making neutrons that make more split, that make more neutrons. This can only form a critical chain reaction, critical meaning that it's self-sustaining, if there's enough of these uraniums, because the neutrons fly off in random directions. So see how like they fly off in random directions? If you have a big enough mass, each neutron can actually hit, you know, more and more. You know, if on average more than 1 neutron hits another uranium atom, more of them will split, and more of them will split, and you end up with a critical mass, and you end up with what's called criticality, which means that it's going to self-sustain. The reaction is just going to keep on going. Neutrons making more splitting, making more neutrons, making more splitting, making more neutrons, so on and so forth. It won't happen when it's small enough. That's called a subcritical mass. This is a critical mass or a supercritical mass. Yeah, so it's the critical mass of uranium or plutonium or whatever you have that's fissile. The word for something that can sustain a chain reaction is fissile. I'm going to show you a quick little demo of that, a little game that I like to show off for critical mass. So just a sec. So I found the game. It's a great time-wasting website. It's called Chain Reaction. I'll put a link down below. But this is basically a good way to show off criticality, right? Every reaction can make another reaction. So I'm going to try it over here, right down here. See how I make a thing, and each thing can make a thing. Right. And so you've got this nuclear chain reaction where neutrons give off neutrons, give off neutrons. This one's, you know, it's not exactly the same because it's like an explosive radius rather than anything else. But that one didn't work. You know, if I could try somewhere else, Maybe if I wait until there's a high concentration of these somewhere, I can get a better, a better chain reaction. So maybe if I wait until these guys converge, right, and I can get a better result. And as it goes on, it gets harder and harder. Yeah, great game though. Pause. I'm going to go back to the thing. Yeah, so here's the back to the note, and yeah, that's critical mass. That's chain reaction. So the idea behind a nuclear weapon is you want to take something from subcritical to supercritical very, very quickly. So here, what you might have is a gun type. It's called a gun type fission bomb. You have 2 subcritical masses of uranium-235, and then just a straight up explosive over here. And when it explodes, right, the one goes into the other, and now that's a critical mass, and then the whole thing blows up. It's important to note that when this happens, a lot of energy gets released, a lot of thermal energy gets released, and so the whole thing blows itself apart, and only a tiny bit of it actually does fission before the whole thing blows apart. For example, this was the type of weapon used in the first nuclear bomb on Hiroshima, and it only did, I think, 1.7% of its material. 1.7% of its uranium-235 actually ended up splitting. The other 98% were just kind of vaporized and spread out. So that's a gun-type nuclear weapon. The much more efficient type is an implosion-type weapon that actually uses explosives. The yellow here are explosives. The explosives are shaped to go off all at once, and they make a shockwave that comes in and squeezes the core. And then the core, from a shell like this, ends up as a small ball, and that's the critical mass, right? That brings it down to a critical mass. And those are more efficient. Those the Fat Man, the second nuclear bomb, was an implosion type plutonium weapon, and it delivered something like 20% of its energy. The fission reaction was about 20% of the plutonium. But the most efficient nukes use something called boosted fission, which is an explosion type device, just like this explosion type device, but in the center is a little bit of tritium gas. And tritium gas is hydrogen-3. It likes to kick out neutrons if it undergoes nuclear reactions. So this explodes, a nuclear reaction starts, the nuclear reaction compresses the tritium releases neutrons make more nuclear reaction happen. And then you get a very, very, very powerful explosion in a small thing. And then the even bigger ones are thermonuclear weapons. So they use a nuclear reaction, a typical nuclear reaction, an implosion type device, to implode a secondary reaction. So they use normal explosives to compress this to make a nuclear reaction happen, to make a chain reaction happen. That blows up, and the power of this explosion compresses this, and it's a fusion fuel. And so you end up releasing a bunch of energy from nuclear fusion. Nuclear fusion releases more energy per gram than nuclear fission. It's a lot. It's like 1 billion joules per kilogram. It's insane, and it blows up. So it's a primary and a secondary. It's actually 2 bombs in one, but the second bomb can't go off unless it's ignited by the first bomb. So it's a 2-stage thermonuclear device. These require a lot of mathematical modeling to make sure that this explosion can set off this explosion. And so they need supercomputers to do it. So access to that kind of stuff is incredibly classified. But the general theory has been well understood since, the 50s. So I can, show you that. One really funny thing about these types of weapons is the theoretical best material that the best guess people have as to what's actually around the 2 bombs is just polystyrene, just styrofoam. It just makes me laugh that nuclear bombs are full of styrofoam. For just kind of funny. Yeah, the casing itself is reflective, so neutrons will bounce off the casing and come back in, which means that you get more yield, because instead of leaving, the neutrons just bounce right back in. And that's a nuclear chain reaction. So those are nuclear bombs. Next up, we'll talk about how that relates to nuclear power plants. I'm going to pause and fix this stuff up. Okay, so we're on to nuclear energy generation, nuclear thermal energy. As mentioned before, it's just a standard thermal energy reactor. It heats up water, the water turns into steam, the steam drives a turbine, the turbine drives a generator, and then out goes the electricity to the grid. But the difference is that this is created by a nuclear reaction. So they want this to be critical. They want the reactor to be critical, but not too critical. So they have to carefully manage the reaction, the chain reaction. If it's subcritical, they're going to lose power. If it's too much critical, they heat up the water too much and they can end up with an explosion. There are many safety mechanisms. That's what we're here to talk about. So they want to stay very close to critical, and there's two ways that they do this. There's moderators and control rods. Moderators and control rods. Moderators moderate. So if you think about like a moderator in a debate or a mod on a forum, a moderator on a forum, on an internet forum, they make sure that things are going the right speed. So a moderator will actually slow down the neutrons that are getting released by the fission events. The weird thing is that actually speeds up the fission reaction, because really fast neutrons, when they hit the nucleus, they might not make it do the right fission reaction, or they might just kind of glancing blow off of it. Slow ones have a better shot at being absorbed. There's actually a unit for the absorption of various forms of radiation by nuclei, and that unit is barn, as in like hitting the side of a barn. It's one of those funny physics units. So yeah, that's moderators. They slow down neutrons, but that actually speeds up the reaction. So you can modify how fast the reaction is going by changing how much moderator you have in your reaction chamber. So more moderator will make the reaction go faster, less moderator will make the reaction go slower. But the more important thing is control rods. Control rods will absorb neutrons. So they lower them in, and you see that there's less nuclear energy getting released. They take them out, and more neutrons are flying around, so there's more of that criticality, and so more energy gets released. So the control rods are pushed up and down using a computer. You see these control rods here going up and down. And yeah, they're pushed up and down automatically to keep the reactor at the power level that they want. Yeah. So now that you know about control rods and moderators, there were two major nuclear accidents in the world so far. I'm not counting 3 Mile Island. That was tiny compared to these. The biggest one was Chernobyl in 1986. What happened was they were doing a safety test. They took out all of the control rods, and at the same time there was a failure of the cooling system. And so the reactor got too hot and the control rods were all out. And they scrambled to put them back in, but due to a flaw in the reactor design, they accidentally made the reaction go faster very quickly, and then it created a huge steam explosion because these things are heating up water. And there was a lot of deaths because of the radiation exposure, because people weren't ready for that explosion. And then they had to go in and decontaminate it and everything. A lot of people died from the decontamination work. There's a whole mini-series about it called Chernobyl. Please watch it, it's super cool. The other one was Fukushima, 2011, so 9 years ago now. What happened there was it was a normally operating nuclear power station. It was, old, but not that old. And there was a tsunami and an earthquake, so a big earthquake and then a tsunami. That cut off the power supply to the cooling for the reactor. And without the cooling, the fuel got too hot. And if the fuel gets too hot, you can have an explosion. So nuclear reactors have backup systems. Fukushima had backup generators. Problem was that those backup generators got got hit by the tsunami, and so they didn't have their backup generators. That's okay. They had a backup to the backup. Those were emergency batteries. So they had 48 hours of emergency cooling power to keep their reactor cool. So, in a normal circumstance, that would be enough time to ask the government to bring in, trucks, or to bring in some kind of generating thing. It's not a big generator that you need to run the cooler. Not like that big, obviously, but like, truck size generator would be enough. But because of the tsunami and because of the difficulty in getting there, there was no time to reconnect the power, and there was a steam explosion because the cooling power got shut off. It was a smaller explosion. It was better managed. The power plant had a better design, but it was still an accidental radiation release nonetheless. Bad enough that people still can't live permanently near the reactor. It's a relatively small area near the reactor, on the order of maybe 10, 15 kilometers around the reactor. Much smaller than the Chernobyl exclusion zone because that was a much bigger explosion. So how do our Canadian nuclear reactors, this is the CANDU reactor, it's the one that designed by Canada and actually exported to other countries around the world. So we get a lot of, we're pretty good with the nuclear power here in Canada. Here's some of the safety features that it has to prevent these kinds of issues. First off, they've got these shut-off rods. So these purple ones are the shut-off rods. They're permanently raised up above the reactor, and if there's a sudden loss of power, or the computer decides that it's a bad, they're getting bad readings and stuff, they just let these drop. So no power is needed to drop these. You can do it manually. They drop in and it very quickly shuts off the reactor. There's also this injection system of poison. It's not like human poison, it's poison for neutrons. It's stuff that absorbs the neutrons and messes up the reaction. That also doesn't take power, it's actually pressurized. Right, so think of like a fire extinguisher. They just spray this stuff into the reactor, and it quenches the reactor. It stops the reaction from going on. They've also got this cool backup cooling cycle because this gets hot, and when it gets hot, the water starts circulating through convection. And so they have a system where they just add water, and in the design, it's designed so that the convection brings the water back around. And so they don't need electricity to cool the thing. It kind of circulates itself. All they have to do is keep adding cold water and taking away the hot water, and it cools itself, which is pretty cool. And if all else fails, it's in a huge containment structure. Right? It's in a big containment structure. So there's this really thick concrete shell over it, and if it does blow up, this is rated to withstand any kind of explosion that this thing could possibly throw, essentially. They've got other things to do, other things as well. There's like a whole building that's just empty, and it's connected to this one by a valve. So if it's getting too much pressure in the core, they can actually just vent it to that building. It's a big vacuum tank, basically. There's all kinds of other stuff. They're also extremely well trained, and they've got really good computers and stuff like that. Let's talk about the advantages of nuclear power. First off, you get a lot of energy. Nuclear reactions release a lot of energy. Fossil fuels are somewhere in the range of tens of thousands of joules per kilogram. This nuclear energy, just fission, uranium fission, 76 million joules per kilogram. So thousands of times more per kilogram than the fossil fuels. So you don't need to mine as much of it. There's also lots of uranium in Canada. There's no greenhouse gas emissions except for the building and the mining. So they're big buildings. So they do take a lot of energy to make. But over the course of the lifetime, they overtake basically anything else. Nuclear is one of the lowest in terms of greenhouse gas emissions over a lifetime. It's a very, very steady power supply because, the reactor is just constantly pushing out thermal energy day and night. It's very, very, very rock steady. And some nuclear reactors can be used to make medical isotopes and make useful things. So some of them have, ways to put in samples to irradiate them and then pull them back out, and then that sample can be useful. Disadvantages, number one, the very, very long time to build. It takes 10 years basically to build a nuclear power plant. It's a very high cost to build as well because it has to be very precise, very, triple, quadruple checked. Also a high cost to operate. You need specially trained technicians, like really, really specially trained technicians. There's always that potential for radioactive release, no matter how good our safety systems are. There's always a chance that there's that perfect 1 in a million situation like in Fukushima, right, where they had all these backups, but they all failed. And the last piece is even if you don't have an accidental release, there's still radioactive waste. They need to put in fresh uranium 235. So the stuff they pull out needs to be stored for a long time. And we're not talking about like a few years. We mean thousands of years before it's safe. So that's an ongoing problem. Most of the time they just dig a big mine storage facility in a very geologically safe zone, like somewhere in the middle of the continent where there's not a lot of earthquakes or any of that, and then they just store the waste there. But try convincing someone that that's something that you want to build in their state or in their province. Maybe you'll have a difficult time with that. So that's disadvantages. And there's also a public perception disadvantage, so we should probably add that in. Public perception. Bad PR due to Chernobyl and Fukushima. I guess capital F, capital C. All right. Next up, fossil fuel thermal energy. We already really covered how this works. Coal or whatever is burned for energy. Oh, I guess I should fix the current topic. So, fuel energy. And I should fix the top. I'm going to pause. Right, so fossil fuel energy is, second to last energy source we're going to talk about. Fossil fuel thermal energy just burns, stuff to make heat, turns a turbine, turns a generator. You've heard that before. But the advantages of these, like some places still build these, a lot fewer now. But first off, it's relatively cheap. The energy source is still relatively cheap. Oil is still cheaper than making a solar panel, but it's getting very, 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 very close. You also get quick and very powerful energy generation. You just start burning the thing, it very quickly turns into steam. You don't have to start up a nuclear reactor or anything like that. It's also much faster build time than dams or nuclear stations because you just need some way to put something flammable in there, and that's basically it. And they can also use capture technologies to reduce pollution. So theoretically, you can recapture that carbon somehow and store it. Disadvantages to this, they release greenhouse gas emissions during their entire lifetime, and over that entire lifetime, including the build costs of all nuclear plants, they release about 50 times more CO2 than nuclear plants, and about 20 times more CO2 than solar, than large-scale solar. So they release a lot of greenhouse gases. You need to spend money getting the fuel, so if oil and coal and natural gas get more expensive in the future, these plants get more expensive to run. They're also a non-renewable resource, so they need the mining sector. You need to pull stuff out of the ground, which is why the fuel costs are going to vary. And the last piece here is that it releases other pollutants into the air, including, interestingly enough, more radiation than a nuclear plant releases into the air. Because the smokestack, the smoke that comes out, includes some of the uranium and thorium and stuff that was in with the coal. And so that ends up in the air. It's not enough to really worry about, but it is actually interesting that they release more radiation into the air than nuclear does. Of course, overall, nuclear produces more radiation and radioactive isotopes, but in nuclear, those are in solid form and they can go into their storage area. Yeah. Last type of energy here is geothermal. Very, very straightforward. The ground is hot. Pull in the hot water. It turns into steam. Steam turns a turbine. Turbine turns a generator. Generator makes electricity. Put the water back in the ground. Water heats up. Comes back up. It's very simple. Advantages here are there's no energy source needed. The ground is the energy source. It's just always there. And it's a constant flow. Day, night, whatever. It's just the hot earth that you're pulling energy from. Disadvantages is that it's a relatively low energy output and it can only be built in very, very specific places. So hot spots in the crust where there's a lot of heat close to the surface. Yeah, so for example, there's a lot of these in Iceland because they have a low population, so the low power generation doesn't really matter. And they also have a lot of volcanoes and they have a lot of hot spots. So that's geothermal, just a standard thermal energy site, just depends on where the energy comes from. Yeah. Now the last piece here is peaking and storage. I'm going to pause. Okay, so the last piece here is peaking and storage. Keep in mind here that electricity will actually change in price throughout the day. So this is why we're interested in peaking and especially in storage. This is a graph of the energy generation from various sources in Ontario for the last week. So starting 25th March and going to today, March 30th. And the orange is the nuclear baseline. Remember I talked about how nuclear is a very steady source of power? Well, our nuclear plant is pretty much, plants are always just making like 10,000 megawatts just consistently. Hydro, you can see the hydro here ramping up and down a little bit. So hydro can actually ramp up and down pretty well during the day. Now you can see here that those are like a really nice quick response to the amount of demand that was filled in by hydro. Wind, when you look at the wind energy, it really depends on how much wind there was. So here's a day when there wasn't a lot of wind. Here's a day when there was a lot of wind. And wind was able to keep up the slack, take up the slack on this day, but not on this day. So this dark blue had to pick up the slack. And the dark blue is fossil fuels, natural gas power plants here in Ontario. And they're used to fill in the peaks. That's called peaking. So a peaking power plant, it only turns on when it's time to fill in the peaks. So you see that most of the time it's not on if we're making enough electricity. The dark blue is very, very small. But when it needs to, it can ramp up very quickly because all they have to do is throw more natural gas in there and it'll make more electricity. You can't do that with solar and you can't do that with wind. It's harder to do with hydro at speed. So, hydro is harder to spin up the turbine than these guys are to react. So it's faster. And so we still have fossil fuel burning power plants, mostly for this peaking thing, for the peaking that they can do here in Ontario. Yeah, so that's peaking. You can see the solar. There was some solar here and some solar here and some solar here, but not a lot of solar here when it was rainy over the weekend. Yeah. Now, a recent thing is energy storage, large-scale energy storage. So here's a plant in Australia, and it's a giant bank of batteries. It's a huge, huge, huge amount of batteries. And what this does is it takes in energy when it's cheap. Remember, it changes in price during the day. So it pulls in electricity when it's cheap, maybe at the dips in the demand curve. Down here, there's less demand. So you buy up electricity when it's there, and then you release it back to the grid on the peaks. And so this thing can actually kind of cover for the peaks, and it's even faster than a typical power plant because it's just a battery. It's already in electrical form. It's already electrical energy. So, technically it's chemical, but it's a very fast conversion. And so that's the Tesla energy storage plant in Australia, and it's been saving them a ton of money, tens of millions of dollars a year. They save just by grabbing electricity off of the grid when it's cheap and putting it back on the grid when it's expensive. They have reduced their greenhouse gas emissions. They don't use their natural gas plants or coal plants as much because of this thing. So we might see more of those in the future. Another kind of storage is kind of cool. It's called pumped hydroelectric dams. So a normal hydroelectric dam has a big reservoir and then another place where the water's actually flowing through. Here, they pump it up into a reservoir, and then when it's time for them to get energy back out, it flows back down and drives the turbine. So when electricity is cheap, you use electricity to push the water up into the reservoir. And then when electricity is expensive, you let the water back down, and it drives the turbine, and you get electricity. This is really cool because you can do it in old mines. Right? Mines have very, very big, deep shafts, so you have an automatic high and low reservoir. Kilometers. This is a kilometer of mine shaft. So Germany is going to convert one of their old coal mines into one of these, and we might see more of those in old mines as well. And they're adding wind power to it and solar power and some other stuff. I think that's kind of cool. Pumped storage is used in Britain to quickly add energy to the electrical grid, especially when everyone is making tea, which is kind of funny. It actually turns on right at tea time so that people have enough electricity for their kettles. So yeah, that's electrical concepts, electrical generation concepts. Let's review. We talked about basic power generation and the importance of turbines. The turbine down here. Turbines turn linear energy into rotational energy. Generators turn that rotational energy into electrical energy. And the generators are very, very efficient. Turbines are not so efficient, especially turbines that have to deal with gases. We talked about solar, hydro, and wind and the various advantages and disadvantages of them. We took a detour into nuclear weapons design. There's a Wikipedia page that'll teach you everything you need to know about it. Then nuclear power generation, and some of the safety features that our reactors have. Then some other thermal energy plants like geothermal and fossil fuel, and then this last thing about peaking and energy storage technologies. I've been talking for long enough, so thanks for watching, and I'll see you guys in class.